All right, so this is 127, and we are down to the second bit of Windows overflows, and then we're going to move these other factors. There was going to be a guest speaker, but the guest speaker is not going to come on that day, so I filled in the missing sections here with the more chapters in the book, which are good things to cover. And last time, Caitlin gave that demonstration of that Python tool that writes your own shellcode, and I got some of that working, but I haven't got it polished enough to make a finished project yet. I think I should have that ready by next week. I spent all day struggling with it and kindly got it working with Caitlin's help. So today I'm going to demonstrate some other projects, but by next week I should have that write your own shellcode project working. So let's start with the slides, which I should have open someplace. There they are. But yeah, other people do have Cobalt Strike in their courses, so it can be done, and maybe I can do it too. All right. So we're going to talk about stack protections, heap protections, and other overflows. So GCC is the open source compiler used on Linux, and so if you compile, remember we did this thing, a simple Linux program with a buffer overflow in it. So if you compile that thing, you compile it by default. It will be compiled with a stack protector. When you add the -f stack protector switch, it will compile without a stack protector. And you can see the one, I made this PWDP, and you can see it's a little bit different size. Although I thought it would be smaller, but it looks like it's bigger. Anyway, it's somewhat different size. And when you disassemble it, if you look at the one with the stack protector, it has these options here. See, here's the prologue to get you into the, I think the vulnerable subroutine. And see here, it just pushes the old base pointer, starts a new stack frame by taking the old base pointer and putting it in a stack pointer, then subtracts 24 from it to make room for local variables. Now it has a new stack frame, and now it starts doing things. This one here also has these extra commands moving something from the GS segment up. And what's that doing is copying a value from this location, GS plus 14, which is just a random value. And it's putting it at the end of the stack frame, so that if there's an overflow, it will detect that. And when you go to the end of the routine, this one just leaves and returns. This one first calls stack check fail local to see if that value it stored when you first entered this routine is still there when you're trying to leave. And if that value has changed, it will not attempt to return, because that means attacker may have overwritten the return value and it shouldn't be trusted. So that's stack cookies. All right, we also call that a canary value, placed at the end of the stack to detect if there's been a buffer overflow. Notice, by the way, that this will not protect you from the kind of buffer overflow where you overflow one local variable into a different local variable. It will only detect if you overrun all the local variables and get down to the stored return pointer, which is, of course, the most dangerous kind of attack. But it doesn't stop all buffer overflow attacks, just those, which are the main ones you want to stop. And so the stack protector in Windows was developed later and pretty much is an imitation of the Linux protection. So if you take the same program and compile it with write it in C++ and compile it with the command line compiler, you can compile it, and we'll do it later in the demonstration. You compile this program, and then you add the GS minus switch, which will turn off the stack protector, and therefore you get two versions of the program, password with the stack protector and without, and the one without is a little bit smaller, about 500 bytes smaller. Same general story as the one before. And so if you disassemble it with IDA free, you'll see here is the security cookie code. This takes this security cookie value and moves it into someplace on the stack, and then this one doesn't. So this is the one with the security cookie protection, and this one doesn't have it. It's just the same story. So that's Microsoft C++. The GS compiler flag is on by default, and what this does is it puts those security cookies on the stack, although it doesn't put them in every routine. It puts them in any routine that seems at risk, which, as I remember, it checks to see if you have a character array larger than 5 bytes or 10 bytes, something like that. That's the only situation in which it figures that you're likely to have the opportunity for a buffer overflow, and it doesn't put it in every routine, although there is another flag you can turn on to force it to put a stack cookie in every routine if you want to. It doesn't put it in all the routines for performance. So that places a 4-byte random value after a procedure call check before the return, and that protects the base pointer and the return address. So you could only have the weaker kind of overflow that we've talked about before, where you might be able to leak from the name into other variables, but you won't be able to hit the saved EBP or the saved return address without tromping on the security cookie. And since it's 32 bits of random value, if you were to just try to get lucky, it would take 4 billion guesses before you'd have a good chance of randomly getting lucky and guessing the right value to put there. All right, but that would assume that the value is completely random and unpredictable, and it might not be as random as it should be. This is a flaw in many Windows defenses, that the random number is not really random. So here's how it does it. It takes the date and time, process ID, thread ID, the tick count, and the performance counter, which is just several different clocks, and combines those numbers together with XOR, trying to get an effectively random number. All right, so if you can run another process on the same target to get those time variables, then you can predict some bits of the cookie. And so there was a study checking the percent accuracy, and they were able to predict about half the bits in the cookie. So it should have been 32 bits random, but if you are able to get that timing information, you can get it down to 17 bits of random. So instead of it taking 4 billion guesses, it'll be 2 to the 7 times 1,000. So that's something less than a million, like 1/8 of a million. So I guess 100,000 guesses would be more like it. So it's still a defense of some sort, but it's not quite as strong as you might think it should be. All right, there we are, 100,000, that was the answer. All right. So the security cookie value is put at a careful position to protect the EBP. That's this calculated position here where it puts it, carefully making sure it's at the end of where all the local variables are stored and before the base pointer and the return value. And there's the epilogue modification we saw, where it calls this security check cookie routine. All right. And so that compares it to the authoritative value that's stored in the data section. And if that fails, it'll call a security handler. And the security handler will, of course, just cause the program to stop with some kind of error message. All right. Now, before this GS flag, local variables were placed on the stack in the order of their declaration in the source code. It just put them in the order the developer put them there. Now, in an attempt to increase security, it carefully puts all the arrays at the bottom of the list so that you are less likely to be able to overflow the end of an array and hit another local variable. The only thing you would hit would be another array if there are multiple arrays. And this is probably a good idea because the arrays are holding things like names and passwords and things like that. And you wouldn't want to hit the other values that contain like numbers and Boolean values, which might be, are you administrator? Yes, no. That's the idea. This lowers the odds that you're going to leak out of a string array and overwrite something that's really important. All you're likely to overwrite is another string array. So that's the game here. Here's the original thing, name, password is admin. You might have this, but the modern version of the compiler will put the is admin here and just have name and password here. So your name can leak into password, but nothing in general is probably less dangerous. All right. We could, for example, other ways to attack it, if we can find a way to overwrite the authoritative cookie value, then we could pass the test. If we can overwrite the handler or the pointer to the handler, we can cause it to run code of our choice when the check fails, and that would be good. These are ways to possibly defeat it. I'm not aware if there are any attacks that have succeeded in doing that, but they might have. This defense has been around for a while. All right, and then the heap. The heap is a place where you just store temporary data that might have varying lengths. So you have HTTP requests coming in for a web server, and each request has to be processed, and then you want to free that memory for the next one. So the request could be big. So the logical thing to do is put that on the heap. Now, every process has its own process heap, and there's a function to get a handle to the process heap, which is also stored in the process environment block. And last time, Caitlin was talking about the process environment block and the thread environment block, which contain useful pointers, so your process and thread can find the data structures it needs to find. So this code returns the pointer in EAX. So you can get it from the FS register, FS30. I think Caitlin was in fact using that last time. So, all right. The Microsoft default functions in the Windows API tend to use the default process heap. You can create more heaps if you want to. They're all inside the process heap, but you can create a separate heap for some special purpose. So you can have the default heap here, and there's a heap count, a list of them, and the process environment block sends you to the start of the default heap. And there might be other subheaps linked up in here, or it might just be all running in the default heap, which is what you'll find with Windows API calls typically. So you use heap allocate to borrow a chunk of memory on the heap, and there are older versions, local and global allocation. So this, you allocate some space, you tell it how many bytes you want to allocate, and when you're done with it, you call heap free to release that chunk of data that you've reserved. The stack grows downwards, the heap grows upwards. It starts with list entry structures that keep track of free blocks. Since the heap has blocks of different sizes created and destroyed as you go ahead, it suffers from a fragmentation problem, just like your hard disk as you write and delete files. So you can have like chunks of unused space sort of scattered through there. So it's a doubly linked list like this. So you have data stored here, and each node has data, and it has a forward pointer and a reverse pointer. The forward pointer goes to the next heap chunk. The reverse pointer goes to the previous heap chunk. So if you free a node in the middle, then it has to mark this data available, and then it has to update this forward pointer to skip to the next one. So it has to take the data from this chunk, telling it where the next pointer is, and put it over here. And it has to take the data from the backward pointer from here and put it over there. Now this means if I was able to overflow this node, this data, and overwrite those pointers, when this chunk is freed, it will take data that I changed and write it to where it thinks the next pointer is. And this, anyway, as we've seen, and we did heap exploitation before, the point is if you have an overflow in the heap, you get a chance to control a write operation where you control both the data that is written and the address it's written to, which we learned how to exploit by overriding pointers that will eventually end up in the EIP. All right. There's quite a lot more to it on Windows. The Windows heaps are far more complicated than the Linux heaps we've been exploiting, but the general principle remains the same. So you can override a pointer to the exception handler with that write operation, or to the unhandled exception filter, or a pointer in the process environment blocks. These are various ways to do it. All right. So here's a thing called RTL release PE block, or intercritical section. This is every time you exit a process. That's one option. And Windows 2003 server doesn't use these things, but there are other pointers we can attack. And I don't want to struggle too much over the details. These heap attacks, they get very confusing. Windows XP brought in vectored exception handling, which we've talked about. So there's a series of exception handlers and pointers to them. And those are the structured exception handler registration records we saw. You can overflow them with a heap overflow. So you can also try to get the unhandled exception filter, and this will be exceptions that are not handled by anything in the structured exception handler at the last resort. You can, in principle, overwrite that. I'm not sure this has actually been done, though. So your overflow corrupts the heap, and you'll probably, when the heap is used by the code later, you'll probably have an error. So one thing you can do is just make the heap into a single heap with no other data on it. That's one simple way to clean it up. And I mentioned before, but the one thing I know is Cisco routers have a process called check heaps, and they just hop through all the forward pointers to the end, and then through all the backward pointers back to the beginning, and make sure the whole heap is intact. And they do that every few seconds. And if that ever fails, they just reboot the router, throw away everything, and start over to prevent people from exploiting heap overflows. But Windows systems do not have a check like that. Just like the stack, which we've corrupted, it will keep on using it until it triggers a normal exception to cause it to stop. All right. So anyway, if you're changing exception handler, you're going to have to repair it when you're done with your exploit, or you may, of course, crash the program. And this is partly why, like I was saying in the news section, when people are attacking you with malware, they often cause things to crash, and you might find crash reports that warn you that you're under attack. Now let's talk about COM objects. These are objects sort of like DIL files. They're different in structure, but they have a similar purpose. Your program creates an instance of a COM object when it's needed. There's a library of available COM objects, and when you need one, it loads it up in memory for you to use, putting it on the heap. In the same way that when you call a library function, it will load the library into memory and connect to it, although libraries do not go on the heap. So, all the COM classes have these things called interfaces, and those point to vtables, and these point to the available methods. So it's a lot like a library. And they contain data. There's data fields in there, and these data fields might have overflow vulnerabilities, and if you do, you could overflow into the next object's vtable and change the pointers that point to the data structures. A lot of these are vulnerable. They've been around for a really long time. They're really old. They see thousands of COM objects are available, and that Microsoft adds them to a kill bit list. There are over 600 known vulnerable COM objects in the Windows ecosystem. And what happens is they don't remove them. They just add them to the kill bit list, and there are ways to circumvent the kill bit list. Here's a Ole COM object viewer I ran on a Windows machine, and it gives you a clue how many there are. Many, many categories. .NET, Active Scripting Engine, many, many categories, each of which contains many, many COM objects. There are a lot of them. All right. And other things you might overflow. If you have a data section that just has these global variables, you have a buffer, and then you have a couple of other integer things. If you're able to overflow the buffer, you could change these pointers. And you could, in principle, overflow structures in the thread environment block or the process environment block. That would be pretty amazing to change where it thinks the locations of the memory segments are. There are no examples of that exploit, at least as of the time they wrote your book. But in principle, that could happen too. All right, let's take a look at a Kahoot, and then we'll go to the demonstrations. This is 127, Chapter 8b. All right. In order to get an A, we need a total of 527 points. That sounds correct. It's in the canvas. I just put the total there. You'll find it in an announcement at the top of the canvas. And I'm waiting for people to sign up. Let me see if I can get there. Yep. It's a good question. Everybody, at this time, we're coming to the end of the semester, and everybody's always trying to figure this out. So I will do it now while waiting for people to join the Kahoot. Just have to go to Canvas. City College, there it is. All right, I'm nearly there. 127. Announcements. There we go. So there it is. Yep, 527 for an A, 468 for B, and so on. Right there at the top. So anybody should be able to check your scores and figure out how much you need. Good. I'm glad you reminded me of that. That's always an important issue this time of year. All right, let's try these Kahoots. Good? Yeah. Anybody that's doing the extra credit should have a pretty easy time getting an A. All right. So which defense is the canary? All right, that's a security cookie, another word for it. I think canary is the Linux term and security cookie is the Microsoft term or something like that, but it's all the same thing. All right, so what do the Windows API functions use? They use the process heap, not the other one. The default heap they tend to use. All right, so what kind of data is stuck on the kill bit list? Yep, those are the COM objects. All right, which API call is most likely to be exploitable after a heap overflow? Yeah, it's when you free a heap chunk that it's most obviously going to lead to a write operation under your control. All right, so which item is created when needed by another program? Those are the COM objects. These other things are created when you launch a program, but when you call a COM object, it creates an instance of it in the heap. All right. Mm-hmm.